Welcome back, everyone. I hope you enjoyed lunch, had nice conversations. You're all fine so far? Have an interesting day, right? Okay, I want you to introduce you now to Kurt Stockinger. You've seen him on the video before this morning. He's a professor of computer science, director of studies in data science on ZAW, and he's co-head of the ZAW Data Lab. His research focuses on data science, on big data actually, natural language query processing, query optimization, and quantum computing. Well, curious? Please, the stage is yours. Kurt Stockinger, welcome.
Thank you. So, hello everybody. It's the first talk after lunch break, so we have to take it easy, even though it will be a very hard topic. Okay, so that's why it's also challenging. So the topic today is quantum machine learning and what can we actually do today. Okay. Those people who had visited the keynote speech yesterday, one was supposed to say something unusual. And the unusual thing that, in my case, I have a twin brother, so this is no joke. So this works perfectly for a quantum teleportation problem. So what are we talking about? This is one of the big grand challenges in sciences, if you will. This is a tokamak. This is currently being built in the south of France, so close to Côte d'Azur, beautiful place. And the problem that is supposed to be solved here is fusion energy. Okay, and if you can solve the fusion energy problem, you solve a lot of energy problems. The problem is now, in order to make this energy, you have to put much more energy in there to get it out. Okay, so there is still a big dream, and we're still not there yet. So it still requires a lot of scientists, physicists, engineers to build this. But I trust in the physics. This will come at some point. Okay, you have just a little bit patient. Next thing, which is also a big dream and is also coming closer, is this kind of machine. It looks beautiful. It's a quantum computer, and this is a quantum computer developed by IBM. And what we want to show today is what can you do with these kind of machines? They're in the news all the time, and what can you actually do with these machines practically, and which problems can we solve, okay? So, the outline of the talk, I will tell you a little bit about what is quantum computing, what is this beast behind, what is the theory behind this mystical thing, how can we actually program a quantum computer, and then in the end, how to program quantum machine learning. So machine learning is already a super hot topic, as you have seen, and it's sometimes not so easy to understand, the black box. Quantum computing is also difficult, so take two difficult things together and it becomes extremely difficult. And that's why it's also interesting, because we want to solve really hard problems, not the easy ones. You know? The easy ones can solve someone else. We focus on the hard problems. And since many big brain cells are here, so we can together solve the hard problems. So, this gentleman is Richard Feynman. He got the Nobel Prize in Physics in 1965, so some time ago, and he's considered the father or the godfather of quantum computing. Okay? Was at Caltech at this time, and he did something about quantum dynamics. And so basically, most of the theory goes back to this gentleman. Okay? The downside it is, and he says here, I can safely say that nobody understands quantum physics. So that's good. I'm a computer scientist. I worked at CERN for many years. So this means if I don't understand everything, that's okay, because apparently no one does. If not even a Nobel Prize winner understands everything, whatever you can tell me or ask me, if I don't understand, if I cannot answer it, it's okay. If I could answer it, I would be lying, according to Richard Feynman, okay? Because he cannot understand it. But let's see, maybe you can understand a little bit, okay? This is a few years ago, so maybe we're a little bit further. So where are we in terms of quantum computing? In 2019, Google published this paper on Nature, and Nature is basically the place to be as a scientist, and they called it then quantum supremacy. And this is a term which is not supposed to be used anymore. Now you call it quantum advantage, and this is when a quantum computer is better than a classical computer. And what did they show here in 2019, and this is quite interesting, They used a 53-qubit system, whatever this is, we will show a little bit afterwards. And they could demonstrate that they can solve a task on the quantum processor shown here, which would take 200 seconds. And on a classical computer, they claimed it's 10,000 years. So how can you solve a problem which takes 10,000 years on a classical computer in 200 seconds on a quantum computer? So this is what Google claimed. Which a few days afterwards, IBM said, yeah, if you optimize the classical one, you can bring it down to 2.5 days. So from 10,000 years to 2.5 days, I would say that's quite a bit. But 2.5 days and 200 seconds is also quite some difference. So there is something. Now the question is, which problem did they solve? And the Google guys are extremely smart, and they chose a very good problem, and they built basically a random number generator. What do you want to do with a random number generator? You want to choose random numbers, right? This shouldn't follow a specific distribution that you can predict. They should be random. Now, quantum computers, as we know today, they make noise. If you generate random numbers that introduce noise, it's even more random, right? So you solve a random problem with a noisy problem in an even more random number generator, and it's perfect. So it's the perfect problem for actually this, for this kind of solution, okay? What do we have today? Of course, when the tech giants compete against each other, there's hopefully some technological advance. And now the most powerful and the quantum computer is from IBM. It came out in November 2022, so a bit more than half a year ago. It has 433 qubits. And IBM is supposed to come out with a new one with 1,000 qubits, maybe this year, we will see. So this is cool. What happened, maybe you have heard it in the news, a week ago, New York Times article says, quantum computing advance begins a new era. So IBM published a paper in Nature last week, not using this 433 qubit computer, but a smaller machine, 127 qubits, and they solved a specific problem and material science problems. And they could show also that on the quantum computer, they are in some cases even better than on the classical computer. Okay, so this shows we can solve some problems. It's a material science problem. You can read, there is a nice podcast on Nature, which is easy understandable also for the layperson. So I recommend you read it or listen to it. And they say they didn't gain any new insight into materials. So from the point of view of material science, it's not a new insight, but from the point of view of quantum computer, it's a big step. Okay. So the question is now, this you hear in the news, you know, things are going well. Now the question is, what can we actually do with this, and how do these things work? And to understand this, we need to basically go through this concept. So we want to understand what is a quantum bit or a qubit, what is superposition, what is entanglement, and how to build a quantum circuit. Don't worry, I will not present any formula today, so you don't need to have a PhD in quantum physics, but I will explain it to you in easy things that you can hopefully understand it. So, what is a classical bit? In a classical bit, typically you switch, you have some energy, it's 0 or it's 1, so on the left side that's a classical bit. You can store zeros or ones. A computer is nothing else than just a big storage of zeros and ones, and if you do it smartly, you can get a large language model and you can train ChatGPT on it. But in the end, it's just bits, zeros and one. A quantum computer doesn't have just zeros and ones, but it has something in between. So it has quantum bits, and this is basically, it's in a superposition, meaning it can either be 0 or it can either be 1, and possibly even at the same time everything together. You might heard of Schrödinger's cat, so the famous physicist who did this experiment where a cat is in a box, there's some radioactivity in there, and the cat could either be alive or dead, and here it's a little bit similar. So, but what does it actually mean? We can think of a qubit on something which is a sphere. Okay, this is the Bloch sphere. Bloch was a Swiss physicist, and he came up kind of with this analogy to explain what quantum computing is a bit easier. So typically what we have on top, it's a state, a quantum state, and this can be 0. So this is like similar to a normal bit is 0. Below, you have 1. Okay? So this means the state is 1. On the quantum, on the sphere, you can have all possible states. So this means you just don't have just 0 or 1, but you can have everything on the sphere. Okay, so this means the number of possibilities, the states that you have are like all the points you have on the sphere. Okay, the notation is a little bit funny. So this funny sign here, it's a psi, and it represents in quantum mechanics a state or an energy. Higher state is higher energy, lower state is lower energy, and this is actually like a tensor. So this strange thing with a pipe and some bracket, it's called a bracket notation, and this is like a tensor. Maybe some of you have heard about TensorFlow. I suppose everyone. Very famous neural network library from Google. So here we also have tensors. Okay, so see, quantum has a tensor in the machine learning. We also have a tensor. So this is one thing you can basically say superposition. You can have all different states together. Next thing, what is important in quantum computing is entanglement. And this is a very powerful concept, which is maybe most of the mysterious things we can think in modern physics. And I explain it here with 2 dice, because as you know, Einstein said, hopefully God doesn't roll a die, but maybe this is also not quite true. So assume we have 2 die here, right? So this is 1 die, and this is another one. And suppose I rotate this 1 die, okay? What happens to the other die here? In the normal world, does anything happen? No, right? You roll 1 die and the other one doesn't change. So this means nothing, because they're just 2 independent dies. What happens in quantum computing or in quantum mechanics? If you roll 1, you also roll the other one. And this is what is the concept of entanglement. So you can think of them, these are like particles or spins, and they are entangled. So basically there's a correlation between them. If you change one, you also change the other one. And it cannot just be over a distance of 3 millimeters. As Anton Zeilinger, who got the Nobel Prize in Physics last year, showed, you can even do it over a distance of meters, of kilometers, and so on. And you can not only just entangle 2 dice or 2 spins or whatever you want, you can entangle 20, 50, or 100. Okay? So this is also a very powerful concept. We don't quite understand why it works. We don't know, is it a force or whatever, but it just works somehow. Okay? So then these are the things that we can use now for actually programming a quantum computer. So with this together, you can then build what is called a quantum circuit. And the quantum circuit is a little algorithm that you want. Okay? And what kind of operators do you have? Like in normal computer science, you have an AND gate and an OR gate. So these are really on the hardware implementations of the computations. Here you have what is called quantum gates. And one is called the Pauli gate, named after the physicist Wolfgang Pauli. These are the gates where you rotate, this vector that you have in your sphere, and you rotate it around. Okay, so basically it's a rotation which is similar to like a matrix conversion, if you will. Okay. Then you have a Hadamard gate, and this Hadamard gate basically brings superposition. So superposition that you have all the states potentially all at the same time. And the next one is a controlled gate, and this is with the control gate you can do entanglement. Okay, so everything what we said before from quantum computing, rotation, superposition, and entanglement, and you basically need these 5 gates. So this means the way of what we program, now we have specific gates. How does it work now? So you have these gates, how can we actually use it? Nice thing, IBM open sourced what is called the Quantum Information Science Kit, the KISS kit, in 2017. So since 2017, we can all program quantum computers. Quick question, who has ever programmed a quantum computer? If you're ready, very good. If we inverse the problem until next year, also the other ones will program. It's super fascinating, so you should try it out. So what can you do? Below here is the 3-liner of Python code that you do for doing the smallest quantum circuit that you can think of. And I want to use 3 different kinds of gates. So the X gate, a rotation around the X-axis, a Y gate, a rotation around the Y-axis, and the Z gate, a rotation around the Z-axis. Okay? So how do we do it? So the notation that you have, This Q stands for a qubit, and this X is for an X gate, okay? And if you want to program it in Python, you say, I use the Qiskit library, I use a quantum circuit, and I use the operator on the quantum circuit, I use the operator X, so this is a rotation, and then I draw it. And if I draw it, I see here this is a very small quantum circuit. So what we do in a quantum circuit, you have a qubit, you have some rotation, and then you measure. The problem is, when you measure a quantum state, it can be first in superposition, and if you measure it, as we know from the Heisenberg uncertainty principle, suddenly all the different states go into one. So you have either 0 or 1. So basically, when you measure, you disturb the system. So you lose all the parallelism. That's important. With superposition, you can basically say you have a super powerful parallel machine. And with entanglement, you can have then correlations among all the calculations. So parallelism and cross-correlation. These are the main principles. So what does it actually mean? Let's say here again we have the Bloch sphere, we have a vector which shows up, okay, a vector or a tensor, and now it shows up, qubit 0, it means it's in state 0. Now we apply the X gate, so we rotate this thing around the X-axis. So we just do such a rotation. As we see now, the arrow points down. Now it's from the state 0, from the quantum state 0, it goes to the quantum state 1, okay, on one qubit system. Now we can say 0 and 1, okay? Let's try another gate. Let's try the Y gate. So we have now the original state. We apply the Y gate rotation. It's the same thing, okay? Because you see here, here's the X-axis, here's the Y-axis. You can either turn it like this, or you can turn it like this. It also goes down, okay? Let's try the Z gate. Who has a guess now? I have the Z-axis. The Z-axis is the one which is vertical, and I rotate around the Z-axis. What will happen? Let's see the answer, nothing, because if you return in the same axis, nothing happens. So in this case, we're unlucky. In this case, nothing happens, okay? Why is this important? Because you can apply these different gates, and depending on which states you are, they have an effect or not. Let's go a bit more. Now let's get superposition into the game. With the Hadamard gate, was a French mathematician, we now bring our system in superposition. How do we do it? Again, here's the source code, quite simple quantum circuit. On the quantum circuit, I use the function h, which is the Hadamard gate, and then I draw it. Now what happens here? We do a rotation, and now, before the arrow showed up, this was state 0, state 1, now it looks at you. And this is superposition. Why? Because it's somewhere between 0 and 1 could be all the potential states in between. So just this one rotation with the Hadamard gate, we now have superposition. And you can think of it a little bit like probability theory. So quantum computing is just a very highly parallel probabilistic machine, if you will. Okay, so you can think of it. So that's why if you flip a coin, you can either have 0 or 1, 50%, and now we are here in between. But it's not just 0 and 1, it can be all the potential states in between, okay? So now let's do another circuit. So now we have Hadamard gate, we do superposition, and then the Z gate, we do a transformation. Let's see what happens now. Here we have superposition, and now we rotate around the X-axis. So basically, we just do a rotation like this. And then we see the arrow goes into the other direction, and you rotate it by pi. You know, 360 degrees is 2 pi. A rotation by pi is a half a rotation, so it shows in the other one. This means you change the phase of the system, okay? And now this is the most complicated slide I have here. How do we do entanglement? And as I said, entanglement itself is a super complicated problem. How do we program entanglement that you can also use it? And there what we use, a C-NOT gate. And C stands for conditional, a conditional NOT gate. And what it does, it says, I need 2 qubits. Now this is a 2-gate bit. And if one qubit is in the state 0, I change the other one, okay? So how does it actually work? So you see here, on top you have qubit 0, and in top you have qubit 1. And 1 is the control bit, and that's the one on top, and the plus is the target bit, okay? And then what happens is, and here we have the logic behind it. So you say, in the input qubit, if it's If it's 0, then don't do anything. And if it's 1, it's 1, then change the target bit. Okay? So you can see, can I actually use here the laser? No? But you can see on the right side, you change, depending on in which state 1 qubit is. If it's 0, don't do anything. If it's 1, change it. Okay? So this means now you can do the entanglement. And in this case, you see the code. I do CX 0 and 1, so you have 2 qubits, and then you apply this. And you can, the nice thing is now you can chain it together. If you have 2 qubits, you can entanglement. If you have 3 or 4, and you can entangle it, and then they're all kind of correlated. Okay? So now I've done quantum computing in 15 minutes. Now you should be all experts, and with this one, and I'm not joking, with this one you can start programming. Okay? And that's actually, let's see what we actually do. And the idea is, we don't want to do it just for fun, we want to solve a machine learning problem. And the idea is that we say, take the main concepts from quantum computing, superposition, meaning super highly parallel machine, entanglement, cross-correlation, you can everything, and use the effects that you have from quantum computing and from quantum mechanics, and use it for applying it to machine learning. The thing is, the 10 years ago, I remember first time we had this conference, it was a guy from MIT said, data science is in its infancy. I would say quantum computing is even more in its infancy. So this means there are a few theoretical approaches and a few actually work, and we will show how you can actually do it. Okay? So, let's take a neural network. And we take just one of it. I don't need to explain your neural network. You're all experts on this. So let's take it apart. On the x-axis, you have the axis, and these are the inputs. Then you have one output, the y, and in between, in this neural network, you have hidden layers. Okay? So now one of the ideas is, how do we actually now turn this into a quantum neural network? The problem is, currently quantum computers are quite full. They are quite noisy. So this means you can keep the superposition maybe for a fraction of a second, and afterwards you lose it again. So this means you can only do very short calculations. So you have to use it only for small problems. So the question is, implementing a whole neural network is currently not feasible, because first of all, the quantum hardware is too small, they are too noisy. But, and that's the good thing, you can combine it in a hybrid approach where you say, take the classical algorithm, where classical is good, and just replace the kernel or some parts or the most complicated part with a quantum circuit. And this is exactly the idea here. So let's say in between these hidden layers, I replace it with a quantum circuit. And you will see afterwards it's a parameterizable quantum circuit. So you say the hidden layers in between, they are connected to a quantum circuit. So now the output of the hidden layers are 2 different quantum states. This is psi1 and psi2. Then what you have see in between here, this R, this is a rotation, can be a Pauli gate, X rotation, Y rotation, and so on. Then you measure the results, what you get from the quantum state, and then the results go back to the classical neural network, to the hidden layer, and then measure the whole thing. Okay? One approach, just replace one part of the neural network with a quantum circuit. The question is, what is a good quantum circuit? Okay? The other extreme case, do everything on a quantum circuit. And that's kind of interesting. So on the y-axis, you see all the qubits. So from qubit 1, qubit 2, qubit 3 to qubit n. And then in between such a quantum circuit, you just apply the quantum gates, rotations, entanglement, superposition. That's all that you have. And if you look, this kind of also looks like a network, right? So the abstraction in neural networks, you have the inputs and the hidden layer, everything is connected with neurons, and here it's actually quite similar. So you don't have a network, but you have a circuit, even though it's not really a circle, it goes all linear. And if you have an Adama gate or these uniform transformations, it's just matrix multiplication or tensor products. So similar to what we have in a neural network, you have the inputs and the weights, and you multiply them, and hopefully by smart or clever network architecture, neural network architecture, you get a good result. Here you can do something very similar. So this means a quantum circuit can be considered as a neural network, and the neurons are basically the connections between the qubits, and you have the operators of the gates that you have. Okay. So this sounds all quite good. So how does it actually work in reality? And up to now, maybe go back one second. So the big optimization problem is, as you know, in neural networks, you have to find what is the good weights and what are the good biases, and then you do grid search, parameter optimization. In fact, you do brute force all the parameters until you find the best one. Now, this goes one step further. You still need to do this for the neural network, but also the parameters here. And the parameters in a quantum circuit are, first of all, what combinations of quantum gates do I use? I have only 1 more minute. Okay, we do it in 1 more minute. Or what are the angles that you use for the rotations? Okay, so let's speed up a bit. What we did, we said let's try it on a specific data set, and we have 5 different data sets. One is about rain, the other one is something else. So you will see small number of records, only 500, and the goal is to do a classification. For instance, on the rain data set, can we predict rain or sun? Okay. And then what we did, we implemented it on a quantum simulator, on the classical machine learning algorithms, and on IBM's quantum computer. How do the algorithms look like? So we experimented with different ones. On top, you see one specific quantum circuit. You have 3 qubits, you do some rotations, you do some entanglements, you do some other rotations. So you see, if you look a little bit abstract, it kind of looks like a neural network, but now it's a quantum neural network. Circuit 2 looks very different. So you do first all the rotations, then entanglement. Or circuit 5 is even more complicated. First rotations, and all these R and Rx and Ry is rotation around the x-axis and the y-axis. And all this, in the end, is vector matrix multiplication or tensor product multiplication. So it's essentially, it's very similar to what we have in neural networks, just on quantum hardware. And hopefully we can take advantage of the nice benefits that we have on a quantum computer. So how are the results? And this was actually quite surprising for us, that we said, for these 5 data sets, what is the classical neural networks, what is the accuracy that they can have in predicting, is it rain or not, or is it a specific area? You see, on average for these 3, we have like 78% accuracy. And we can see on the quantum simulator, we have even a little bit more, so like 8% more accuracy. This is on the simulator, and then we want to see what is actually on the real machine. And then you see it's like 85%, very close to the actual. And I have to leave in a minute. Here, of course, we are scientists, so we have to do error analysis. So you see all the different algorithms, all the different implementations, parameters. You see there is a quite range. We can do the error bars. I can show you in a second. We have published this, so you can read it up. Try to find some flaws, and if you want to work with that, we are currently experimenting on new things. So what summary? I think what you can do nowadays with quantum computers, you can solve small problems. So I think we are in the stage where it's not just a physics problem, where physicists build machines, we can actually use them. This KISS is open source. You can all access quantum computers. You have all access to 7 qubits. You might need to wait a bit in the queue until you run it. Sometimes it takes 10 hours until you run a small circuit. But you can play with it. You can solve small problems. Can we solve big problems at the moment? Not so much. But the combination of classical computers with quantum computers, assembling them in a smart way, I think it's quite challenging and quite promising. The important thing is, I've seen 3 or so have been using it. Currently, the market and the competition is still very low because it's a quite tough entry barrier, understanding this quantum physics and the math. You might get a little bit demotivated when you see this, but you can forget about all this. If you just take the few ideas that I had here, you can actually use it. And the important thing is, the earlier you start, the better you are. If you do this thing in 3 years, everyone has done it, as we have seen with ChatGPT. Okay? So I think you will. No? So if you have kids, I have 2 small kids. One is 6 years old, and the other one is 8. And my wife is also a physicist, so we got this book, Quantum Computing for Babies. It's a very good start. It explains how this is a ball, this is, and so on. So I think hopefully we'll get this also for quantum computing, and then if you need to know a bit more than this, we can have a chat. Okay?
and maybe they will solve some problems, most pressing problems of human mankind.
Exactly.
All starting with that book.
Exactly.
Thank you very much for being here. This is for you.
Thank you.
Thanks a lot.
Thank you.